Helicopter Flying Handbook 1-1 Introduction to the Helicopter. Helicopters are captivating aircraft, lifted and propelled by horizontal rotors, each composed of 2 or more rotor blades. They fall under the category of rotorcraft or rotary-wing aircraft, distinguishing them from fixed-wing counterparts. The term helicopter originates from the French hélicoptère, coined by Gustave de Ponton de Macourt in 1861, linked to the Greek words helix or helikos, spiral, or turning, and pteron, wing. The primary advantages of helicopters stem from their rotor blades, providing lift without the need for forward movement. This unique capability allows helicopters to hover, take off, and land vertically, making them suitable for congested or isolated areas where traditional runways are impractical. Piloting a helicopter is a demanding task, requiring focused and safety-oriented training. It involves continuous attention to both the machine and the operating environment. Pilots must navigate in 3 dimensions, utilizing both arms and legs constantly to maintain control, requiring coordination, timing, and control touch. While helicopters were developed earlier, it wasn't until 1942 that Igor Sikorsky's design reached full-scale production, with 131 aircraft built. The single main rotor with an anti-torque tail rotor configuration became widely recognized as the standard helicopter design. In 1951, Charles H. Kaman made a significant advancement by modifying his K-225 helicopter with a turbo-shaft engine, marking the world's first turbine-powered helicopter. Turbine engines offer less vibration, increased performance, reliability, and ease of operation. This innovation played a crucial role in the subsequent development of larger, faster, and higher-performance helicopters. The versatility of helicopters stems from their ability to take off and land vertically, hover for extended periods, and navigate effectively under low airspeed conditions. Consequently, helicopters are employed in various tasks such as transportation, construction, firefighting, search and rescue, and more. This scene illustrates some of these applications, including search and rescue, firefighting, and construction. In summary, helicopters have evolved significantly over the years, finding diverse practical applications due to their unique capabilities. From their early designs to the adoption of turbine engines, helicopters have become indispensable in fields that demand agility, precision, and versatility. The helicopter rotor system is like the powerhouse that makes helicopters defy gravity. Picture this: the rotor can be mounted horizontally, lifting the helicopter up vertically, or vertically, like a tail rotor, providing that horizontal thrust to counteract torque. And then there's the tilt rotor, where the rotor is mounted on a nacelle that can smoothly shift from horizontal to vertical, offering a versatile and dynamic capability. Now, the rotor trio consists of the mast, the hub, and the rotor blades. The mast, a nifty hollow cylindrical metal shaft, rises from the transmission, playing a crucial role. At the mast's top, we've got the hub. It's like the VIP section where the rotor blades get attached. Speaking of rotor blades, there are various ways they can hitch a ride on the hub, and that's where classifications like semi-rigid, rigid, or fully articulated systems come into play. It's like rotor blade fashion, but for helicopters. But wait, there's a twist in the story. When the engine cranks up the rotor in a single main rotor helicopter, a sneaky torque effect kicks in, making the helicopter want to spin in the opposite direction. Enter anti-torque controls, our heroes fighting the good fight. You've got your classic tail rotor, the cool Fenestron also known as a fantail, and the futuristic NOTAR system. It's like the Avengers of aviation, but for helicopters. Now, let's talk about the common practice of having a single main rotor but needing a sidekick to deal with torque. Igor Sikorsky was onto something when he designed the VS-300 helicopter with a tail rotor, setting the stage for the helicopter design game. And to keep things simple in our chat, we're sticking with a counterclockwise rotating main rotor system. No need for a tail rotor drama here. Those counter-rotating rotors cancel each other's torque like a power couple. And don't even get me started on coaxial rotors, they're the Russian rock stars in the helicopter design scene. Picture this. 2 rotors turning in opposite directions but mounted on the same axis. It's like a synchronized move, and the Russian Kamov helicopters have mastered it. Last but not least, we've got the tail rotor, the unsung hero at the helicopter's back. It's a smaller rotor, vertically mounted, dealing with torque like a champ. The tail rotor drive system, with its gearbox and flexible couplings, is the backbone of stability. And when it comes to forward flight, that tail rotor isn't just hanging around, it's doing some serious power moves. In the intricate world of helicopter flight control, 4 key maneuvers take center stage. The cyclic, positioned between the pilot's legs, often referred to as the cyclic stick, functions akin to a joystick. Robinson helicopters come with a unique T-bar cyclic control, and some models have overhead or side-mounted cyclic controls. Its magic lies in its ability to adjust the pitch of the rotor blades throughout each revolution, tilting the rotor disc and guiding the helicopter in different directions. A forward push on the cyclic results in a forward tilt, propelling the helicopter in that direction, while a sideways push leads to graceful lateral movement. On the left side of the pilot's seat, the collective comes into play. Equipped with a friction control to prevent accidental adjustments, the collective serves as a magic wand for altitude control. By simultaneously changing the pitch angle of all main rotor blades, it orchestrates ascent or descent. Pulling up on the collective prompts all blades to lift, providing upward thrust for an ascent, while pushing it down facilitates a controlled descent. The anti-torque pedals, akin to rudder pedals in fixed-wing aircraft, take their place in controlling the helicopter's direction. Located in the same position, they serve a similar purpose, steering the nose of the aircraft. Applying pressure to these pedals alters the pitch of the tail rotor blades, influencing thrust from the tail rotor. This adjustment causes the helicopter's nose to yaw in the direction of the applied pedal. The pedals mechanically adjust the tail rotor's pitch, influencing the amount of thrust produced. Completing the quartet is the throttle, acting as the conductor in this aerial symphony. Whether it's a twist grip on the collective control or lever mechanism, the throttle regulates the power produced by the engine. This power is then transmitted to the rotor through a transmission. The throttle's primary function is to ensure the engine produces enough power to maintain the rotor RPM within the optimal range for lift during flight. It's the delicate balance required to keep the helicopter's performance in the sky both harmonious and precise. Together, these controls form a harmonized team, seamlessly coordinating to navigate the helicopter through the skies. In the realm of helicopter flight, two fundamental conditions come into play: hover and forward flight. Hovering, often considered the most challenging aspect of helicopter piloting, involves contending with the gusty air generated by the helicopter itself. This turbulent air acts against the fuselage and flight control surfaces, necessitating constant control inputs and corrections from the pilot to maintain the desired position. While the control inputs in a hover are straightforward, involving the cyclic for horizontal drift, the collective for altitude, and the pedals for nose direction, the challenge lies in their intricate interplay, requiring constant adjustments in a cyclical pattern. In a hover, manipulating the cyclic forward eliminates horizontal drift, causing the nose to pitch down, increasing airspeed, and leading to a descent. Conversely, pulling the cyclic aft pitches the nose up, slowing the helicopter and inducing a climb. As the helicopter reaches equilibrium, the horizontal stabilizer aids in leveling it to minimize drag, distinguishing it from the pitch deflection observed in airplanes. The precise coordination of cyclic, collective, and pedals in a hover demands accuracy and constant correction. Adjusting the collective while maintaining a constant airspeed allows for controlled climbs or descents. Coordinating collective and cyclic inputs facilitates changes in airspeed while maintaining a constant altitude. Pedals play a crucial role in maintaining balanced flight, aligning with their function in fixed-wing aircraft to center the ball in the turn and bank indicator. This topic offers a comprehensive overview of the helicopter's history, its diverse applications, and its evolutionary journey. It introduces fundamental terms, elucidates helicopter components and sections, and delves into the theoretical underpinnings of helicopter flight.